received a very kind invitation. I was happy with. I started thinking, and Lucy asked me this, how many people have I actually worked with over here? And so I started making a list of the people that I've interacted with. Of course, you know, Luis Felipe has all these papers, right? So just by random chance, you know, his cross section is large. And then I've got a few papers with Enrique and a paper with Humberto. And of course, my main collaborators are, well, I'm sort of doing something with Laurent, but as he says, as he told me yesterday, I'm not very much use. Yeah. So mostly I work with Paola, and most of the talks are going to be about Javier. And then there's one more category, friend. And, of course, I never win these arguments, as you all must know. So the title has to do with kind of, I want to say a little bit about my evolution, personally or professionally. That I got into things with molecular clouds and stuff, but I was originally a stellar astronomer. And so I started working on T-Tauri stars because they were magnetically active, and so on. And then there was a long story with disks. But I was very interested in this paper by George Herbert, where he said that when he was looking in Taurus, you should have more older stars than young stars, because most of the stars were 1-2 million years old. And so how could this be? Because things should go down the Hayashi track. And he said that, you know, it's a source of some unease that this large population of what he called post-T-Tauri stars, the older stars that should have been there, haven't been found. So he did this paper, and he didn't find it with this particular technique. So I thought I'd try it. And did a proper motion survey with Kurt Jones and John Stauffer, and we didn't find them either. And then, you know, not willing to take no for an answer, did something with Cesar, with large follow-up of Schmidt plates, and we couldn't find the older stars either. So that was, so I was stuck. You know, what was going on? How could this be? And the point really was that if you looked at Taurus and you thought about a crossing time, the ages of the stars were considerably less than the time it would take to communicate information from one end to the other of the cloud. So the breakthrough came when Paola and Javier visited CFA. This is a picture from long ago. You can see some of us have degraded considerably. So there's Paola with some CDs, I don't know. And then there's Javier. And some fairly sexy lady over on the right. So anyway, so in the course of, Javier was supposed to be working with Alyssa Goodman, but he kind of got sucked into our group a little bit, and eventually came up with, he'd been working with Enrique on some two-dimensional simulations of the shearing box intended to represent the galaxy, and they had magnetic fields. And going back to this older paper, this is basically the kind of thing that you saw. So they make density fluctuations, put in some energy for star formation, and then, you know, let it run. And what had occurred to me when I saw this and thought about it is that, of course, what's happening is that the clouds, at least locally, are being made by large-scale flows, and so you don't really have to communicate any information here. It's just kind of accidental that they're built up this way. And so we could solve this crossing time problem. And in fact, you know, it's fairly obvious after the fact there's, as I showed earlier, there's lots of bubbles in the interstellar medium. Stellar energy input is important. Clearly, in Lambda Ori, this is probably a wind or supernova bubble. And I bet you that Orion, which is way out of the galactic plane, has probably been pushed by multiple supernovae. You know, if you just look at the morphology of that. And of course, as there's lots and lots of examples of this, of sweeping up gas, it becomes CO detectable. I'm not going to argue with Ron about whether it's atomic or molecular, but in terms of hydrogen, but in terms of the CO, you have to pile this stuff up. So, for example, again in Orion, A and B, there's the Spitzer stars, Spitzer detected stars, superimposed on the CO. So you've got a distance of about 70 parsecs. And so the crossing time is of order 10, 20 million years, a long way. But the clouds are swept up. And so that's how you can explain the ages are all pretty much the same, right? And I'll come back to this point later because there's actually an important implication of this thing that the crossing time is much, the age of the structure is much less than the crossing time. Okay, so we wrote a paper, and this is basically where we tried to say, the clouds are swept up. And Javier worked on this, and we were trying to see if we could see the H1 to CO transition. So H1 is a big mess, but if we take cuts, so this is the grayscale is the H1, and this is the CO, and so if we take cuts at the same position, and position velocity diagrams, then you can see that there's associated H1 at the same velocity as the CO, but it looked like it was slightly offset, so maybe that could be the inflow. And here's another example of that. So that's the CO, and that's the H1, and so we said, well, this isn't proof of that idea, that we can sweep up atomic gas and make it molecular, but it's at least consistent. Now the other problem that you have is shown here. So this is the Pike Nebula that Charlie Lotta and his collaborators have worked on a lot. And most of these clumps, this is an extinction map, most of these clumps are starless. And probably, in many cases, probably pressure confined by something, which I'll come back to. But even for this wimpy, starless core, there's actually some star formation in one place. And so the point is that there's actually two issues. One is that the ages are low, so you can coordinate them with the large-scale flow. But the other thing is that most of the molecular clouds, and by this I mean CO clouds, in the solar neighborhood are forming stars. And so how can that be, right? So we have to coordinate the thing, and the large-scale flows solve that. But how can we make the star formation occur almost immediately after we've got CO? Because you can't sweep this up in a couple million years. It makes no sense. So how can we do this? And so what we realized was that in this paper that we wrote more than a decade ago, again with Javier, what we found is that basically you need a certain amount of column density so CO doesn't get dissociated. And so if you have this column density and you compare the self-gravity pressure to the average pressure in the interstellar medium, when you get to something about the level where you can shield the CO, self-gravity is important. And so you start collapsing. So that's why in the solar neighborhood, you get this effect where in our relatively low density region, when we accumulate enough shielding, column density, self-gravity is important so you can understand why star formation, at least in principle, occurs. I just want to say that there's been an argument with people like Nick Scoville and so on about whether you have to make molecular clouds from molecular gas, and I guess Ron would argue that too, although H2. And so we can argue about whether, maybe Ron wants to argue whether most of the gas in the solar neighborhood is actually atomic. But the point is, it's mostly not CO in terms of detection. In other galaxies or in higher density regions where most of the gas is molecular for sure, then you can sweep up molecular gas and make molecular clouds. So we were just trying to explain, and that's why we actually had in the title, in the solar neighborhood. Right? So that. Now, there's still another problem conceptually. So it takes, of course, this long time. If you start from low density, it takes 10 million years or so to pile up enough extinction. So, and this is a shock calculation done by Ted Bergen and Javier again was implicated in this work. So we started with H1 gas, and then at some point you get enough pile up so that the CO can form. But the problem then is that you see you have a very slow increase in the visual extinction. In this one-dimensional model, to go from an AV of 0.6 or 0.7 to 1 or so, just in a 1D model, takes many millions of years. So the thing that happens then, though, self-gravity is important, then stuff starts to collapse in some perpendicular direction to the flow. And so then you can have a runaway in the column density. So this is the idea, the calculation that we did with Fabian Heitsch. Actually, he did the calculation and I just trailed along. So there's two flows coming in, and there's a little ripple in the interface just to make some turbulence. So this is the side view, and this is the front view. And so what happens then, as you start doing this, so there's some turbulence. Oops, don't stop. But now you see it starts to collapse on itself because it's got enough mass for it doesn't have big enough velocity dispersion. And so you see you get a runaway. This is a surface density plot, and then you end up making cores. This is not enough resolution to see how messy the structure really is, but basically that shows you the two pieces of the thing. You pile up the stuff, and then it shrinks in some dimension. So these are like 10 kilometer per second flows coming in, and then this collapse velocity is like 1 or 2. So it's like, we're thinking we've got a bubble that's expanding, and if we could do this with a slower flow, it would just slower flow and a higher density or something like that. So that's our story, at least in the solar neighborhood. That you pile up stuff, and then eventually you get a runaway as gravity becomes important, and you shrink the thing down, and that's why you can have a rapid transition from when you have CO with enough surface density to shield, then you can, self-gravity becomes important, you can have kind of a runaway. So that's how you can get age spreads of just a couple million years or so. Now, so there's an interesting implication of this. As somebody yesterday was saying, Ron was saying, there's this thing called virial mass estimates, and where you get the calibration for the X factor, CO, and so on. And to some extent, this sort of works. And the question is why? because if the cloud is less than a crossing time old, then it's hard to imagine it could be in variable equilibrium or anywhere close to it. So the answer, we say, is just that you've got this gravitational collapse. So the difference between equilibrium, Gm over r is v squared, or Gm over r, 2Gm over r is v squared. Factors of 2 don't matter in this business, particularly given the complicated structure. So I think that the reason that the virial masses sort of work is at least in part because you've got this gravitational collapse going, and so there's a relationship between the velocity that you see, velocity dispersions and velocity gradients, and the mass of the cloud. So I'll just show you this toy model that Andy Burkert and I did. Some of you have seen this endless times, but I still like it. So what we did was we took an elliptical sheet. So this is a sheet of gas, this is surface density, and we put a gradient of the density just for fun, and for even more fun, we put a little spin on it. So it's just a 2D model, and it's just some gas pressure and gravity. It doesn't have any turbulence in it, other than rotation. So let's let this collapse for 2 million years, okay? It's 2 million years if I scale it to the size of the Orion A cloud. So it starts falling in, and there's kind of an edge effect which makes filaments, and then we twist it around a little bit, and then we've made that, and there's the 13CO of Orion. Now, I'm not actually going to argue that Orion started out as an ellipse. Right? It's just to illustrate the power of gravity in shaping the clouds, and it's a nice way of making filaments. The other thing about gravity that's very nice is that when you're at the end of a cloud, particularly a massive end, stuff tries to fall into a focus. There's kind of a focus effect at the end, and so you pile up. You can't really see it here, but there's a lot more mass in this thing than this because it's not resolved, but there's a lot of mass. And of course, in many cases, you can see clusters. So here's the Spitzer infrared excess survey, which Tom McGath finally published, and there's the Orion Nebula cluster. So it's not always this way, but oftentimes at the ends of clouds is where you see clustering. And I think that's because of this gravitational focusing that occurs at the edge of a cloud. Okay, so Javier has been continually trying to convince some people that gravity is important in molecular clouds and star formation. And so he did this paper with Enrique to talk about a long-standing issue in molecular clouds, which is that a long time ago, Richard Larson developed a scaling law for the amount of turbulence, or really the velocity width of the spectral lines, as a function of size. And that was supposed to be done with some kind of turbulent effect. And it wasn't supposed to be dependent upon the mass or the surface density. It was just a turbulent thing. And so, pushing on this, we added to a result of Mark Hires, who showed that the so-called velocity dispersion, and this is plotted in kind of a funny way. This is the velocity dispersion divided by the square root of the size for some reason, versus the surface density. There's actually a dependence on the mass, which of course makes sense because, or at least it's consistent with the idea that virial masses sort of work. It's not, now again, it's not that they're in virial equilibrium, but if gravity is important and it generated some motions, then the velocity width, the line widths, or gradients, should be dependent upon the mass of the cloud, or the surface density, and they are. And so Javier added to this with some work by Gibson et al. And the slope, you see, there's a difference between free fall and virial, square root of 2, right? And of course, you know, there are observational uncertainties in these parameters. So the most important result, I think, is the slope of this thing. And so where this comes from, you know, if you do the Astronomy 101 equation, then you get, you know, you write it like that, and then you get this slope. And so it's hard to believe that gravity isn't a major factor in doing this. And so people have tried for many years to try and put in turbulence and then turn on gravity, for instance. And why would you, and of course there's never any idea where the turbulent velocity, I mean clearly there's some turbulence in the clouds. And there's obviously some kind of turbulent structure. But I'll show you that there's a transition in the next slide to higher densities. So the question is, why would you really want to put in a turbulence with a mechanism that you don't know, turbulent velocity, that does what gravity would do if you just didn't do anything? You know, I mean, we don't understand turbulence nearly as well as we understand gravity, so why not, right? So, pounding this into the ground even more, Javier was on a roll here, and so there's something called the column density probability density function, which is a very ugly thing. So basically what you do is you count up the amount of area at each surface density. And generally speaking, you know, there's more stuff at low column densities than high column densities. Each of these tick marks is an order of magnitude. So this is that same simulation that I showed you before of colliding flows, but without any gravity turned on. Okay? And then, so that's the PDF that you get. And if you turn on gravity, so this is the simulation that I showed you actually, where it was collapsing, then what happens is you develop a power law tail due to infall. So you get a power law at high surface densities because of the effects of gravity. And this is actually what you observe. So these are plots from, on the left, we have a cloud that's quiescent, doesn't have any star formation in it, plotted against some log of the extinction, so that's like the surface density. And when you look at star forming regions, if you can go to high enough extinctions, you always see this power law tail. So the story is that turbulence at low column densities can give you this thing that people say is sort of a log normal. You know, and I think Enrique was the first person to show that. But to get the power law tail, you need to have gravity coming in. So you may have some turbulence at low column densities, and I think probably not very large velocities. And then you develop this power law tail, and that's for sure the sign of gravity coming in.
Lee, can I ask a question?
Yeah.
What fraction of the total mass is in the power law tail?
Well, I don't know the answer to that. But the thing is that you can get this rounded shape without having any turbulence. Right? If you just superimpose lumps and stuff, you can actually get this as well without having a turbulent velocity component. So it's hard to know I mean, what I would argue is that this is the signature of gravity, but it's not that gravity is completely unimportant in this part. But clearly there's much in the power law of high surface densities, there's much less mass, right? You know, it's probably on the order of 5 to 10% of the total mass.
I guess it's
At high
the
surface
self-formation efficiency, right?
Yeah, exactly, exactly. Right. But you see, it doesn't mean that gravity isn't important on the large scale. It's just that those are lower velocities, right? Or at least that's my story and I'm sticking to it. So the reason that I think this is important, you know, is not just a technical issue of whether clouds are in like equilibrium or not, but it actually has some other implications. For instance, there are theories, there are a lot of theories to explain the stellar initial mass function. And they all work. So, but the one that I like the best you have to have some kind of fragmentation at low masses. For the high masses, the thing that I prefer is the competitive accretion, or gravitational focusing, if you want, is basically sort of like a dependence like Bondi-Hoyle accretion. The gravitational inflow builds up the big high mass stars. And that's actually a good thing also because we have to make high mass stars quickly. So you need a really fast, very, very, very high infall rate. And the easiest way to get that is just to have a big mass and let stuff fall in as like crazy, right? And so that's consistent with this picture of gravity being important, particularly at high densities. And I think that if the gravitational turbulence in quotes because it's not real turbulence, supports this idea that the high mass saltpeter slope is produced by gravitational focusing. And we actually did a paper with, well, there's a couple of papers. So one of the things that happens when you've got multiple centers of mass and gravity's pulling it in is you make filaments, right? And you can see that in cosmological simulations, right? Same idea. Well, if we do deep extinction maps with CRyA, in a lot of cases we can see that the protostellar envelopes are not very round, but they're actually filaments coming in, which is sort of some of what you would expect. This is a simulation that we did with Gilberto, where we just put some lumps down randomly and let them collect. And again, you can see you get some filaments made. And the other thing that we showed that even in this geometry where we didn't have a cluster, we still got something that was evolving towards the saltpeter slope with a limiting value of -1, where -1.35 is in those units. So this is a very generic mechanism, and it just seems to me like it's the easiest way to explain the universality of that slope, and also that, as I said before, you really need to have very high infall rates if you want to make a 100 solar mass star in 1,000,000 years. Right? So just by having a bunch of stuff around and having it all collapse, you can do that. Okay, now, usually when I give talks, I try and get into a little bit of trouble, as some of you know. So here we go. So what about those groups, right? Well, let me talk a little bit about that, and then we'll see what happens in the question period. So one of the things that we did in that early paper with Javier's early paper, they had the magnetic fields in this 2D simulation, and so of course the flow follows the field. where the field follows the flow, right? Depends on the dynamics. And oftentimes when they built a cloud in the simulation, there was a kink in the field, because as you build up enough mass, then it can kind of drag the field with it. And so what we found is what you might expect, that it was kind of actually hard to figure out the potential energies, the gravitational potential energy. But anyway, the best we could do was that at low densities, everything was magnetically strong, it is subcritical. But then when you got to the more massive clouds, gravity dominated the magnetic field. And this is important because if the magnetic field restrained star formation too much, then it might take many millions of years. So we should see more like CO clouds, with without any stars, until there was enough ambipolar diffusion or reconnection. Now, I think I've modified my views about this a little bit. So I think the magnetic fields are important, but not quite in the same way that people have thought. This is from a recent paper by Dick Crutcher and collaborators. One of the important things is that he argued that actually there's a range of magnetic field strengths, and therefore mass to magnetic flux ratios. There's some very, very magnetically dominated regions and some that are not. But in any event, so this is kind of consistent with flow along the field, because if you flow along the field, you're not really crunching the magnetic field down, and then at some point you get a compression. I would argue it's probably largely gravity, but there must be a transition from the ram pressure to gravity. And so somewhere in here, when you get to molecular cloud densities, there's an envelope here, but actually, if you look at this, these field strengths aren't very much different than these field strengths. So it's only when you get to the really dense stuff that you start building up the field, at least in this data set. So what does this imply? Well, let's take a look at Taurus. And what I want to do is, so here are the optical polarization vectors, so you can see the direction of the field, and you can see kind of actually striations in the 13CO. And I'm going to focus on this filament, which is B something or other. Okay, so you see that the stuff is piled up perpendicular to the field, which is obviously what you would like to do. So let's say we have some field, and then we end here with the star-forming filament. How do we get there? Well, I thought long and hard about this, and then I figured out that we had to pile up the stuff. There's some implications for this, right? First of all, in the pipe, as I mentioned before, there's some evidence that the starless cores need an external pressure. Well, there's enough gravity in this filament to pull the stuff in and provide a ram pressure which could balance this thing. The pipe has the same kind of configuration where it's sort of perpendicular to the field direction. So I think that's where the pressure is coming from, because it's not thermal pressure, it's inflow. And so then the other interesting thing to think about is, as Will said, we have a problem with efficiencies of star formation. They're pretty low. Part of it is that clouds get blown apart pretty quickly. But there's still some issues. And so you can imagine that there's a competition here, right? We have to make the gravity stronger than the field tension and pressure if we're going to collapse and make a star. And so the important thing is that this isn't a closed box system. You can still be adding mass to the thing. And so it might be that the magnetic field, actually what it does is it prevents, not just slows down, but it prevents star formation in some places, depending upon how much mass you've got in the flux tube. So maybe this is a thing that's been suggested by Matthew Bate and others, that the magnetic field limits the efficiency, but there are places where it doesn't really slow anything down. So that's sort of what I'm thinking these days. Just to show you another picture, this is a Herschel, I forget what wavelength this is. Oh, it says 250 microns, so there's the same filament, and you can see these striations. They've marked them in some ugly blue, ugly thing here, and these are the polarization vectors, both from dust absorption and dust emission. And so they argue that these striations are, in fact, infall. And of course, if you have striations, you could very well imagine that you've got variations in the mass to flux ratio in that too. So they even argue that you can maybe see this effect. Here's the CO velocities. They're sort of red-shifted and blue-shifted stuff on either side of this filament, which would be consistent if it was falling in. And in fact, in another paper with Javier, clearly I owe much of my career to him and Paolo. In that same simulation, here are the infall velocities. So it goes, plus 0.6 to minus 0.6 kilometers per second, and you get a ram pressure, which is more or less consistent with what you would need for the pipe course. So if you actually think about how you have to make the dense gas, and if you make it with gravity, you're going to have things like this, where I would say that in a while, and it'll be hard to test this prediction, maybe in another million years or so, more stuff will have fallen into those starless cores and add up the mass, and then they'll collapse and form stars. So we've fixed a couple of problems. And again, this is just for the solar neighborhood. Clearly, we have to sweep up gas and make it dense, and stellar energy input probably modulated by spiral arms. But at least locally, this stellar energy input makes a coordinated star formation. And locally, there's such a close connection between star formation and CO, because by the time you pile up the gas where you have enough shielding for CO, it's self-gravitating. But the final piece of the picture is that, at least in the solar neighborhood, we have to disperse these clouds pretty quickly. And so that's the final problem. And the answer is the way that the clouds get made in the first place, which is stellar energy input. So basically supernova blowing up and evacuating things. So here's a picture of W5 from Spitzer, color-coded with these two IREC channels and the MIPS 24, from paper by Xavier Koenig and Maury Allen. So here are the infrared excess stars in the green. These things, I don't know if you can see it, they're little central dots. They're protostars. And you can see there are various clusters, and it didn't take very, and again, a couple million years. And you blow out holes of, particularly in massive, where you have a lot of star formation, you can blow out 10, 20 parsec holes in no time at all. And the thing is that this will keep going. If you've got stars, if you've got no star there, you've got a bunch of early B stars which can also blow up. So this will keep going and going and going. Unfortunately, calculating this, and I know Enrique's been trying to do some of this, to actually calculate this is not easy. Because of all kinds of, first you have the stellar wind, and then you've got the supernova, and and of course it's a very complicated density structure, and so it's been very, very hard to do this. But I think that's really the next frontier in star formation calculations, and people are trying to do this because, this is also part of the efficiency issue. So this is a hard problem, and it's too hard for me. So, but fortunately, I'm almost ready to retire. So I thank you for inviting me. I congratulate you on a wonderful 10 years. It's a very impressive research organization that you've got here, and it's been important to me. So thanks a lot.
I'm glad we're in agreement. I think gravity and magnetic fields are the two important ingredients. I think the efficiency problem is very serious without magnetic fields. That's been our position. I agree flows must be important when you have to accumulate things very quickly, like in high mass star formation over clusters. In fact, the paper that Susanna Lozano and I wrote wasn't just about ambipolar diffusion, it was about bimodal stuff. So I don't think we're that far apart. I could be another 5 years, I could still be really young. Right?
Well, I don't think so. Because I think, look, there are several pieces to the efficiency problem. One is the finite lifetime of the cloud, right? Because if the clouds lasted for 10 or 20 million years, the efficiencies would be higher, right? I mean, that's blowing up the cloud puts an upper limit to what you can do. Right?
Well, in the inner galaxy, you have a real problem because this is a damage atomic.
Well, I think so. So I think that whether it's atomic or molecular isn't all that important. The question is whether, can you have diffuse CO?
I don't understand that. The first argument was that it's all important. The first 10 minutes of your presentation was that the conversion of atomic to molecular is all important.
No. What I said was in the solar neighborhood. What we were trying to do was explain locally what was happening with CO. And so we started, because most of the gas was atomic, we started with atomic gas. I don't see any reason why you couldn't do the same thing with, having molecular gas swept up, because we were just trying to explain the observational effect, which was the CO. But it doesn't mean that in the inner part of the galaxy, you can't sweep up, more diffuse CO because you've got more shielding there. I mean, it's an interesting question, but I think that you can sweep up diffuse stuff. It's not, what I'm saying is, if most of the gas is molecular, what's a cloud? Right? What is a cloud? Right? It can't all be self-gravitating and collapsing. Now, if you want to do it with magnetic fields.
Why is it?
Because of stellar energy output. It keeps blowing the stuff around. Okay, probably. We can argue about this later.
Yeah, I guess I can add a little bit to this. As Lee pointed out, we've been working on the final episode of this movie, which is the destruction of the clouds by their stellar products. And but so I think before that, one of the important things about picturing this whole process as assembling the clouds and then letting them collapse and then destroying them is taking into account the fact that it's a flow. It's a flow that takes the gas from lower densities to higher densities. And at some point while it's collapsing, the control of the efficiency can occur by not allowing all of the gas to terminate the collapse. And that's what we are hoping to be able to do by the feedback, by the stellar feedback. So far, my graduate student, Manuel Zamora, has performed an analytic model in which we can get the efficiencies to below 10% just by destroying the clouds. And we're working on magnetic simulations in which we're letting the cloud collapse and then destroying them. And so my impression is that without magnetic fields, you can have efficiencies down to 10%, and the magnetic field can give us that extra factor of 2 or 3 that we're
that's what I would say.
But the whole thing is also concerning the molecular galaxies or the galactic center indeed, the point is that whenever you have collapse, the stellar products don't let it turn. And that's how you...
If you try to do it just with stars, you have a real mismatch problem, because stellar velocities are hundreds of kilometers per second. Molecular cloud velocities, once you get the CO density, it's only one.
No, but what happens is when you have...
How does that happen?
Because when the stars destroy the clouds, it's not molecular density.
There's a difference between translational velocity and internal turbulence, right? I mean, you can have a bubble expanding at 10 kilometers per second. You know, if it's the supernova thing slows down and piles up the CO, that part is moving at 10 kilometers per second, but internally it doesn't need to be moving at 10 kilometers per
The
second.
gas that moves that fast is not molecular.
Right.
Lee, I was curious, you haven't actually considered, though, how you get mass onto a central star, is that right? I mean, for massive stars, you have this big problem of you have to produce them on a very short time scale.
Right.
At a rate that's actually, accretion disks are unstable at those kind of rates.
So what I think happens there, right, is that you start with a cloud that's many Jeans masses, right? And so it's not supported at all. So if you think of like the extreme limit of the uniform density sphere, everything hits the center at one instant of time. So if you start with something that isn't supported, but it's got many Jeans masses, it takes a finite amount of time for it to collapse, but then when it hits, you can put a lot of stuff on in a very short period of time.
Well, I mean, by the time you get down, though, to the Jeans mass that actually comes from the star, you still have to worry about how you get that mass onto the central object.
It's just infall. Right? So you have a collapse and you make a protostellar core, but you still have stuff raining down on it. So that's that competitive accretion thing.
Okay, well, I'm as I say,
Well, let's talk the point.